Welcome to the Cosmic Pie Podcast, episode 24, season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Mm-hmm.
We do have a live chat feature that's running, so if you have any comments or questions that you'd like to ask us throughout the podcast, feel free to do so.
Indeed. We will try to answer them anyway.
We will try. And of course, Robert, what we say is...
Just us. It's our opinions and our statements. It's not those of the university or the department or anybody else. We're on the hook.
We do broadcast afterwards. We upload our recordings on Spotify. So if you like that sort of media to look at rather than YouTube, you're free to go there anytime you like, of course. Just give us 15 hours or so to get it up on the...
Yeah, it takes a little bit of time.
You know, you have to wait till like almost 12 hours for YouTube to make this recording available. I think if you pay for it, like subscription, you get it earlier. But we're cheap.
That sounds right. You know, we have no budget here, folks. So
that's the joke about...
Whoop.
That's the
Sorry.
That's the joke about the bird, right? When his cage fell apart, what was the first thing the bird said?
Yeah.
Cheap, 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 cheap. That's what we are. Anyway, so Robert, have you heard of the phoenix? You know where that comes from?
Yes. That's Egyptian mythology, I think.
And what does it refer to?
A bird that dies in flames and is reborn from its own ashes.
You know, we could make that also true with the 30-meter telescope.
That's fair enough. Yeah, it could.
And how that works in that context is
this.
So the extremely large telescopes, and there are two main ones. One is the Giant Magellan Telescope that's being built down in Chile. That's to do observations of the southern hemisphere, so the sky that you can see above Chile at night. The other very large telescope that the United States is part of, as well as other countries, is the 30-meter telescope. And from the name, of course, you can tell the size, 30 meters equivalent in diameter. This telescope was to be, if you like, constructed on Mauna Kea in Hawaii. That's the initial goal. Now, several years ago, there was a political unrest that occurred where the local First Nation people did not want the telescope built on Mauna Kea. In fact, they even blocked the construction crew from going up access to the site itself. And the reason for that is they consider Mauna Kea to be sacred.
Right.
And they did not want someone else placing any more instruments on the telescope. So that's been tied up in legal battle, and a lot of it is true.
Now, I have some insight in there, and will add and make note that when they agreed to allow telescopes and everything to be built up there, there was an agreement made that was basically there would only be a certain number of telescopes. And if you count individual instruments, that agreement has already been broken. So the people were upset. Hey, you said you were going to limit to this number of telescopes. I count this many. And that's not how astronomers see it, of course, because we talk in terms of the instrument, which may be multiple telescopes.
Yeah, in fact, the Keck telescope, the largest telescopes on the mountain, 10 meters in diameter, there's two of them. They have outrigger telescopes that they use, and that's related to trying to minimize the seeing by using lasers. In fact, there's a website that you can go to on YouTube channel. I don't know the address to it, I forget, but you can just type in Mauna Kea live or something like that. And if you do it while it's nighttime in Hawaii, you can actually see the telescopes. And occasionally, and you can see the nice, beautiful sky, and it's clear often in Mauna Kea. Astronomers do not build telescopes in random locations around the world.
Right.
Are you going to put a $50 million telescope, for example, in a place where it's cloudy most of the time?
And the answer to that is no.
That's obviously a waste of money. So they do site testing, and then plus they look at climate data to see where is a good place to put a telescope where, number one, it's clear often. And if it's an optical telescope we're talking about, we want it clear at night. And also something that we call seeing. That's the blurring effect caused by the Earth's atmosphere. In fact, that's responsible for the twinkling of the stars that you see.
Right.
So if you put a telescope in a good location, that would hopefully have minimal twinkling that you would notice.
Mm-hmm.
And Mauna Kea turns out to be one of the best places in the world.
Right.
So if you're going to spend $1 billion to build a large telescope, you want to put it, hopefully, if you can, the best place in the world.
Be where I'd want it.
So if you can go to this live camera once in a while, you'll see lasers shooting up into the sky, and that's using the adaptive optics system, which is a way to try to compensate for the blurring effect of the atmosphere.
They bottom line, they put a laser star of known optical properties on the sky, and then they can flex and bend and distort the mirror shape to counter the distortion due to the atmosphere.
And that requires some much smaller telescope, outrigger telescopes.
Right.
And the other thing that was going to be used for, I believe, is to combine the signals, like an optical interferometer of the two Keck telescopes. And that requires outrigger telescopes as well. And so astronomers would count that as two telescopes.
Right.
But if you have several of these outrigger telescopes, anybody who's not associated with the Keck would count that as individual telescopes. So you quickly reach that maximum number of telescopes that's on top of the Mauna Kea. Now, to be fair to astronomers, and of course I am an astronomer, so I'm talking about myself, there's bias there. Telescopes are one of the sort of least harmful to the environment structure that you could produce.
Right.
So there's not like all this waste product if you're having like a smelting plant or something like that, or trying to extract iron ore from the ground and all of the pollution that goes with industry. Telescopes just want to put the instrument there and look up.
Right.
In some sense, astronomers are mostly people who understand the environment, are hypersensitive to issues of conservation and others. In fact, they go out of their way of making sure that the planet is protected in terms of recycling and this and that and the other thing. So astronomers, at least a majority, are people you want around if you're interested in preserving the natural beauty of the Earth itself.
It's just we got to build these big buildings that.
Now the legal involvement of whether or not the TMT will be located on top of Mauna Kea is tied up, I believe, in court.
Right.
Both the court in the state of Hawaii and everybody is involved into it. I don't think there's a clear path to resolution.
I don't believe so either. I think everything's going to have to end up being renegotiated.
Now, this whole issue, and they are taking down telescopes on top of Mauna Kea because of this. In fact, I don't think they probably would have been deconstructed, if you want to think of it that way, and dismantled and taken off of Mauna Kea if it wasn't for the more awareness of the issues involved. And so astronomers are removing some of the telescopes that they no longer want to support on the mountain for lack of funds or lack of use or whatever it is.
Right.
But still, I mean, this is a sensitive issue, and I don't presume to know all of the issues on one side versus the other, so I'll just leave that. But in some sense, the decision has been made about whether or not to build the TMT, and it was made because a lot of the money to support the telescope has to come from the federal government, and I mean the U.S. federal government.
Right. Yeah.
The idea here is that if you could build two giant telescopes, one in the north, it would cover the northern sky. So in this case, let's say the sky above Hawaii, and then you could build the other telescope in the south. And with the combination of the two, you would basically be able to observe the whole sky. Nothing would be out of reach of these two giant telescopes.
And preferably, and as this is showing, you'd have an overlap region, a significant overlap region.
Yeah, so you have the top part is the northern part of the sky where the TMT would be sensitive to. The bottom part would be the sky that you can see from the south that the Giant Magellan Telescope, the GMT, would be sensitive to. And then there's overlap, which is what you see in the middle darker band of blue. And it's good because you can calibrate each other's observation, and the TMT is not always going to be pointed to the exact same place on the sky as the GMT, so on and so forth. And so there's a lot of benefits to have that overlap. The main point here is that the whole sky would be covered. So if there's any type of sneaky comets or asteroids that are kind of inbound and we want to be able to track those things and have lots of warning ahead of time of whether they're heading in our direction or not, it makes sense you're going to want to have a complete coverage of the sky. And people have heard a lot probably about the Vera Rubin telescope that we've talked about already.
Right.
That's going to cover the southern sky. It's not going to cover the northern sky. So we're going to be missing out on that. The other thing what these telescopes can do is they can do follow-up to different targets, for example, that were picked by other telescopes.
To me, that was the big thing about the two of them is they could follow up on each other's observations. They're going to have similar limiting magnitudes, limiting brightnesses for those rest of you, and things like that. So, they can observe the same targets.
Right. So a substantial amount of money goes into these telescopes. I mean, there is some private donation, but a lot of it is federal government money.
Right.
And because of the federal budget, and I'm not going to argue whether or not that's a good thing or a bad thing, that in the climate that we're in now in the United States, it is to reduce expenses.
Right.
And that includes spending money on these telescopes. So the National Science Foundation, which has been proposed to be cut back itself of money, would support these telescopes in general if you had enough money. Even before the current administration came into power, there was talk that the NSF may only probably support one of the two telescopes. They couldn't afford to support both.
Okay.
So when the present administration made its proposal, they decided that the TMT would not be supported.
Okay.
So it would not go ahead. So it looked like it was lost. And the other thing it did, of course, is it solved, of course, putting it on Mauna Kea or not, that whole question. You don't have to worry about if you can't afford to build it.
Right.
So that all of those problems go away. Now, what has happened is that recently, just a few days ago, Spain has got involved in all of this.
Okay.
And the reason why they got involved in it is because early on, when the unrest started about whether or not Mauna Kea should be allowed to go on top of Mauna Kea, some scientists suggested, well, if we don't put it on Mauna Kea, eventually it doesn't go there, right? Ultimately, we have to put it somewhere else. Where's the next best place in the Northern Hemisphere? And it turns out there were actually two locations I think the scientists were looking at. One of them is in Baja California, part of Mexico, and the other location was in the Canary Islands at La Palma. And there are already telescopes in both locations, so it's not like you're starting from scratch and the infrastructure is not there and so on. These, like I said, you don't put telescopes in random locations. You put them in places that make observing
Clearer and
more
easier.
efficient.
Yeah, more efficient.
And
That's
so,
a good word.
And so there are already telescopes there, both in Mexico and in the Canary Islands. If you look at both places, I think ultimately, and they take a lot of factors into consideration, the government of the host country. It has to be stable. You don't want to spend a lot of money somewhere and all of a sudden they say leave, or we thank you for the telescope, now get out.
Right.
Because we have it, not you. You can think of all kinds of issues that can occur. So ultimately, I think the big push was let's put it La Palma on the Canary Islands if we can't put on Mauna Kea.
Makes sense.
But because of the federal budget then, proposed federal budget, looked like it was going to be wiped out, Spain has stepped in and has offered 400 million euros to put into the TMT project if it gets located at La Palma and the Canary Islands, which is part of their territory.
Part of Spain territory.
Yeah. So they've kicked in big time. In fact, I think this is enough money to save the project.
Okay. Wow.
But
Nice.
the thing is, there's still a lot of push from scientists, especially to try to save the TMT, to ultimately the actual past budget would include money to fund the 30-meter telescope. That's the hope, I think, of a lot of scientists.
Right.
But at least this is a good backup plan. If ultimately the budget, how budgets work in the United States, if you're from another country or never paid attention, is it has to be passed by the Senate and the House. They have to agree to something eventually, and you can go back and forth several times until everybody agrees the majority vote on the budget, and then it goes to the White House where the president ultimately can sign it or not.
Right.
And then it becomes law at that point.
In fact, technically by the Constitution, the bill would actually budget bills have to originate in the House. That's not how it works anymore because people don't follow the rules exactly, but
And
That's
the
what's
other
supposed to happen.
and the other thing I think is if you get a large majority, I think the president can't override or veto the.
He can, but it can be overridden.
It can be overwritten if you have enough members
Enough
of
members
Congress to
of- yeah.
sign it. And so there's all of this back and forth that needs to occur. And you start with the proposed budget that comes out of the White House, and then the Senate and the House look
Yeah.
at it and modify it to what they like, and then it goes on to the rest of Congress to see if they can pass, and then goes back to the White House again. So one of the Senate, but this proposal that comes out of the Senate kind of restores most of the money to
For the
the
TNT.
National Science Foundation. So if you like, it brings the hope back, even if it's only a flickering hope. I don't know exactly the details of this, that the TMT can still be put on Mauna Kea, Hawaii. That is a better site than La Palma.
You're right.
That's
La Palma gets, I know from my DragonCon affiliation, we frequently, during DragonCon, will use a telescope at La Palma, and frequently it will be due to humidity issues or something such as that, will be closed.
yeah.
It has to be closed.
And the other thing is, I hear some individuals always speak up at this point and say, well, why are you debating where to put the telescope? Put the thing in space. Then you avoid all the impact of this. You avoid the impact of the atmosphere. You avoid the issue with satellites, right, that are streaming in your field of view that you have to worry about. But it takes a lot of money to put these telescopes
Right.
in space.
I mean, the telescope itself is going to be several billion, and then you want several more billion to put it into space?
Well, let's look at just aperture size as one indication. This is going to be 30 meters across. The James Webb Space Telescope is about 6.5 meters across, so a lot smaller, and that required like $10 billion.
Right.
So it's going to cost a lot if you scale that up to a 30-meter class telescope.
And it does not scale linearly, folks.
So it's okay to say you astronomers are working in the dinosaur ages. You should be putting your telescope in space nowadays, not worrying about ground. But, give us the money, we'll do it.
Right.
There's no money for that to put everything in space.
Because there's no way around the fact that resolution, the details we can see, scale as the diameter, the radius of the telescope. So there's no way around. We need the 30 meters.
Well, I mean, our University of North Dakota has a beautiful telescope.
Right.
Our department operates the telescope. Give me the money, I'll put it in space.
Absolutely. I would love to have that 20-inch telescope in the space.
But that's the issue, right? I mean, it costs so much to put stuff in space, and that hasn't changed a lot. People are hoping, like the Starship,
Yeah.
that SpaceX, Elon Musk is developing, will lower the cost per pound of putting up material in space, but that hasn't happened yet.
Right.
So-
It was thought that the space shuttle would do that, and it didn't. Sorry, but here it is, folks.
So we should be thankful to Spain for kicking in such a large amount of money and also a site to put the telescope. So without that, I think the TMT probably would have fell apart unless
Right.
something surprising happened. But anyways, we'll see how things play out in the future. We should know relatively soon because this budget stuff will probably wrap up in the next several months,
Right.
and then we'll be able
It should anyway.
we'll figure out where we are and where we stand in all of this. So it's interesting anyway. So thanks to Spain for this.
Thanks for Spain for just showing up and saying, "Hey, we'll do it."
Yeah, exactly.
You know,
Now, the next thing is kind of a subject we've been putting off for a little bit.
we've had this on this docket for a while, folks.
Yeah, so we didn't really get a chance to show it. And this is something known as transient luminous events. This was discovered, I want to say, at least I heard about it maybe 20 years ago or more.
Something like that. Yeah.
And here's kind of the thing that you notice here. So if you ever, this time of the year, at least around where we live, you notice especially strong supercell storms that are nearby. So they're not, they may be gone across or approaching or have already left you, or maybe they're off to the side somewhere, and you can look out the window at night and see all the lightning off in the distance. And you say, what a beautiful sight. I'm glad that we're not underneath that cloud, that kind of thing, right?
That's usually what we're saying.
Yeah, because around here we do get tornadoes and things, so we don't want to be in that situation. So people had noticed, especially if you took, had a camera set up and trying to photograph lightning, that occasionally you see a flash of light, like a tongue of light, that would go upwards towards space, not the lightning going downwards. And people investigated this because once you kind of know what to look for, you can set up your camera with the right exposure times and so on to try to capture these events. And what they are literally licks of plasma that shoot upwards.
Right. So
And they're on top of
lightning that shoots upwards instead of down.
Yeah, and so they're on top of the thunderstorm clouds. So people have gone crazy in the last 20 years because of something kind of cool, and photographs. So lots of photographs of these type of events. They're not unusual nowadays.
I'm going to get into some of the background. It's been noted by photographers for a long time, but scientists and others thought that, no, you're just kidding, because any photographic evidence for it, the cameras weren't that good. The pixel size, the emulsion grain size was large. So anything, it was like Bigfoot. yeah, okay, you got something on there. It's probably a smudge on your lens, okay? So that was going on for a very long time. And then with the advent of digital cameras, all of a sudden your pixel size is down to a few microns. You can get high resolution. You can get exposure lengths of any length that you want. And all of a sudden, bam, here these things were clearly photographed, clearly showing up in the image. And what can you say? Now scientists scramble and start going, okay, well, what could cause this?
Yeah, well, it reminds me a little bit like ball lightning.
Mm-hmm.
You've heard about that. So you see this plasma ball-shaped object, extremely bright, that's associated with thunderstorms. Did you see the video that was taken this summer I think it was from Alberta, where somebody photographed ball lightning?
I have not, no.
Yeah, I seen that. And so it was on the news in the local area, and I noticed it on YouTube. I watched it a few weeks back. And so this phenomenon is pretty rare for it to happen, but it's pretty interesting. You know, these rare things, even though they're rare, they do happen.
They do happen.
And you have to be in the right location, like you said, with the camera. And there are cameras everywhere now.
Right. And that was the other thing that improved the chances of catching one of these events.
Yeah. So this is an image of one of these events taken from the International Space Station. Nicole Ehlers took this. And you can see what we're talking about. So this is a thunderstorm complex on the Earth, obviously. And you can see that tongue of pinkish, reddish light that's come straight up from the top of these things. So there's clearly electrical discharge, flow of electricity occurring. But the connecting wires, if you want to think of that way, is up in the ionosphere.
Right.
To the cloud itself, and you got that transfer of electricity through that pathway, and generating the visible light that we see.
I mean, that's what's neat to me about these things is they're instead of grounding through the ground, they're grounding to the ionosphere, and that's just amazing.
So you could try that yourself, right? You could set up a camera, let's say, on a tripod with a cable connector, so you can take a certain lengths of exposure, and do it remotely so you don't disturb the shaking of the camera. Anytime there's like a thunderstorm that's just off of you,
yeah,
right?
It'd need to be far enough off that you can see the top of
the top of it, yeah.
And you're looking for that anvil shape,
yeah,
where it hit the stratosphere and flattened out.
Just be very careful. We don't want anyone to get hit by lightning.
Oh, absolutely
so
not.
Take a lot of cautions when you're doing this kind of work. But yeah, it'd be neat to get some photographs of that. Kind of cool. Anyway, so yeah, and just to kind of give you an idea of the physics, if you like, a little bit involved, this is a nice graphic that was put together that shows the different type of features that you actually can get. Not only do you have the sprites that both shoot upwards, which is what we've seen on the last picture taken from the International Space Station, but they also have stuff coming downwards. And there's you can see the different features. So you have jets, a different color, you have blue jets, and there's all kinds of morphology here.
Green ghosts, trolls, elves, gnomes, they got really neat, really wild with naming these things.
And the thunderstorm itself is down below, so that's a troposphere. And you can see the connecting upwards to the very top there, about 100 kilometers up, the ionosphere labeled on the left side. So you have, basically, they're conducting wires. You get that conducting path of all this type of phenomena. It's really, really cool when you look at it.
It's neat stuff, and I invite you. This is one of those topics that usually people can get a hold of materials to study and look at, and it's something. Go out and study it. Go out and look up information on it, because it's really interesting how it comes about, how it works, and the different types, what causes the different colors. Because if you notice, most of it's red.
Yeah.
But there is purple and green and blue. and kind of like the same thing
And
with
white too,
with
so,
Aurora.
right. Yeah, exactly.
There is actual chemistry and reasons for these colors to be happening.
Yeah, so if it's dominated by light being produced from, let's say, nitrogen versus oxygen, you get
Right.
different colors.
You get different colors.
Yeah, that's cool.
So it's cool stuff.
For sure. Do you know that our solar system now has a new planet? Well, dwarf planet.
Dwarf planet. Yeah.
There's another one.
Yeah. Okay. We're finding them all the time now.
We're finding them all the time. So here's the latest, greatest discovery. This dwarf planet is cool because it's known as a trans-Neptunian object, which means that its closest point to the sun is further away than the average distance of Neptune to our sun, which is the furthest most regular planet from our sun. Pluto is also classified as now the dwarf planet.
A trans-Neptunian dwarf planet.
So this is way beyond that. This object
Actually, it's not trans-Neptunian because
it doesn't cover.
Closest
It doesn't.
approach is inside of Neptune.
Well, part of its orbit is inside of Neptune. Pluto.
Right.
So that
Sorry, folks.
so it crosses the orbit of Neptune occasionally.
Right. So it's not trans-Neptunian. Yeah.
So yeah. So the thing about this new discovery, and you can see the name of it in the title, Ammonite, Ammonite,
Yeah.
2023 KQ14. There's a mouthful.
So it was found in 2023.
Yeah.
And its KQ14 is probably the group or the instrument that was used to find it, the survey.
Yeah, and the telescope that did the observations that confirmed its nature is a Subaru telescope.
Okay.
That's on top of
Mauna Kea.
Mauna Kea, and it's about 8.2 meters in diameter. So it's not a small telescope, nothing to sneeze at. It's a fairly decent telescope in terms of its operations. Been there for quite a while now, for a couple decades.
Yeah.
I think it first went up in the 1990s.
It's been a workhorse, though.
It has been. It used the latest technology. In fact, if I remember right, they had robots. Right, it's from Japan. It's a Japanese telescope, and they have robots that are in use at the telescope. So a robot would position like fibers if you're doing spectroscopy with the different fibers and stuff.
Okay.
It was the first good use of robots for that technology, which is really interesting. I always think of manufacturing an automobile in Japan, all the different robotic-like instruments that are at play. They're doing spot welding and so on and so forth. And that technology, of course, Japan is highly involved in robotics for many years now, and that came into play here with this telescope, which is kind of cool when you think about it. Now, this dwarf planet, the closest it gets to the sun in its orbit that it has, and you can see there, it's known as the perihelion, 65.9 AU. And AU, Robert, do you want to remind people what that is?
Astronomical unit. It is the average distance from Earth to the sun.
So this is way out there.
That's out there.
And for sake of comparison, the average distance of Pluto from the sun is about 40 AU.
Okay, so this stays out there a good, Saturn, Uranus distance beyond Pluto even.
Yeah, so this is way out there. Now, its aphelion, which is the furthest point from the sun, is about 252 AU.
Wow.
Wonder what the sun, we should calculate how bright the sun would be from that distance.
Well, it'd be a bright star.
It'd be a bright star in the
That's
sky,
it.
but you couldn't.
I don't know that it would have.
I wonder if you could resolve the surface
Right.
with your eyeball.
I don't
It's
think
a half
you
a degree
could.
from the Earth, so you should be able to do that calculation.
Yeah,
and you
not in
go
my head. I'm not.
252 times further out. Each time you go out, of course, it gets smaller and smaller and smaller.
Yeah.
So the apparent diameter drops as the one over the distance. It gets smaller that way, that effect.
Yeah.
So, I don't think you could probably
I don't
resolve
think you
it with
could
your
resolve
eye.
the sun. I think it would be a bright
We'll
star.
have to calculate that. Anyway, so it's really on this highly elliptical like orbit.
Yeah.
In fact, the eccentricity, and you can see that, is 0.7.
0.7.
So
That's
highly
really elliptical. One would be a parabola.
Yeah.
0 is a circle.
Yeah. So it's really a squashed orbit.
It's a really squashed orbit.
Now, the inclination, so how far out of the plane of the solar system, it's actually relatively small. It's only about 11 degrees.
Yeah, Pluto is 13. I
Yeah,
think.
Pluto
Something like that.
is larger than that. And the diameter, now this gets a little tricky because the diameter comes from how bright the object is given its distance. And that depends on how much of the sunlight gets reflected from the surface. In other words, its composition on its surface.
So it's albedo.
So anywhere, if you use sort of reasonable albedo that you would expect for these type of objects to have, the diameter should be anywhere, as you see there, from about 220 to maybe 380 kilometers or so.
Right.
So it gives you an estimate of the size of it. Now, if the albedo is really weird, of course, that would change that number probably significantly.
Right.
But that's the type of orbit that it's in. Now, the interesting thing about this object, and that's what we see on this slide, is its orbit relative to other objects that are at similar perihelion and aphelion, the closest and furthest points. Now, there's a whole family of these objects based on Setna, which was found several years ago. So Setna-like objects are these dwarf. Setna is also a dwarf planet. In fact, it was the object that sparked this whole transformation of calling Pluto a planet and to call it now a dwarf planet, that the International Astronomical Union, the IAU, had a vote on this several years ago to change the designation of Pluto, to the chagrin of Disney, to make it now not one of the major planets. Now, there's a whole argument that can be made to keep it as a planet or move it as a dwarf planet, which we won't get into because that goes down a whole rabbit hole.
That goes down a whole
I think Robert and I are opposite
I
sides
think we're
of
on
that.
opposite sides,
Yeah.
yes.
But anyways, so this is another object that's part of that family of objects that have orbits that are similar to Setna. Now, the figure that you see there on the left, you can see a green sort of dot dash orbit, and then it's a blue color and so on. The one that's just found is
Ammonite.
Ammonite. Why can't they use a name that I can pronounce like
I don't know.
John?
I'm just going to go the green one that's so far out. Yeah, try to pronounce that one. I'm not even going to give that one a go.
No, you can
Not
see,
without hearing it first.
Yeah, you can see the names there. And it's interesting to know that the sun is in that yellow dot you see sort of the upper right corner. And really close to the sun is this sort of bluish or whatever color that's almost a perfect circle from this figure. That's the orbit of Neptune.
Right.
So that gives you a perspective how far out these objects are.
That's crazy.
You're not going to get a suntan laying out on one of these objects. We'll put it that way. Not from our sun, anyway.
Not from our sun. Yeah.
Now, the red orbit is this object, and notice, here's the interesting part. Notice that the other objects there, they're all sort of on one side, in a sense, the bottom part of the sun from this perspective, and that the orbit of this new dwarf planet is above. So it's in a totally different place than the other objects. So its furthest distance from our sun, the aphelion, then, it's way up at the top for this newly discovered object, where the aphelion of the other objects that we've known about is below.
Right. And that's been what they've used to hypothesize that there's a ninth major planet.
Bingo, 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 bingo. So there's this whole argument that people have been involved in for several years, whether or not there's any other major planets beyond Neptune. And to find that, first of all, we've looked, haven't seen it.
Haven't seen it.
And if it is a planet, one of the things it should do is radiate a lot given its surface temperature.
Especially in infrared.
In the infrared. So we've used our best infrared all-sky survey that we have, which is from the WISE satellite, NASA WISE satellite. People have scanned through that data, and also other infrared telescopes looking for signatures of a new planet, and none have been found. And as Robert, as you mentioned, one of the things you can do then is to look for signs of a new planet based on its gravitational influence of objects that we can see. In fact, that's how Neptune
was found.
found. So when they found Uranus, which was done by Herschel in 1700s, William Herschel, what happened was that when they tracked the orbit of Uranus over time, they realized it wasn't in the proper orbit if you just include the gravitational tugs from the known planets and our sun, that it was on a slightly different orbit. And people hypothesized that there must be another planet, probably beyond Uranus, that we haven't detected yet, that's pulling on Uranus, causing it to have the orbit that it does.
And in fact, I can't remember who it was, but there was somebody that calculated where it should be.
It was actually calculated by one person in Germany and one person in England.
Okay.
And the one in Germany is the person that actually observed it
Okay.
first. No, France. Germany confirmed the detection with their telescope. It was a scientist, Levier, in
That's it.
France
Yeah,
that
Levier.
did the calculation and persuaded German astronomers to look at this location, and eventually they found the planet.
Mm-hmm.
It was also done in England, but he couldn't, was it John?
I can't
I'm
remember
forgetting
names.
all this stuff now. I'm getting
I
old.
when you said his name, I remember Levier,
Yeah.
because I remember him when they did find it, him being, of course they found it. It's right where I said it would.
Yeah, based on that gravitational tug.
Yeah.
So, yeah, anyways, so the English person wasn't able to get anybody to look. So John Adams, yeah. So John
Okay.
Adams in England was the one. He couldn't persuade the Astronomer Royal in England at the time to go look. And when and then they've heard about the discovery made by the German astronomer.
Right.
So yeah, it was Urbain Lee Verrier. I can't pronounce the French word.
Okay.
That has got the credit for the discovery of Neptune, but it was done indirectly, right?
Yes.
Here's gravitational pull on Uranus. The body responsible for it should be roughly in this location. Go look with a telescope, scan around that area, you find a new planet.
And like I said, and he was, of course you found it there.
Then you look at Neptune's orbit and see if that has the same kind of effect. Is there some unknown perturbation, gravitational perturbation on Neptune caused by something that you don't know that exists that's responsible for its orbit? And the answer was yes, there seemed to be some perturbation.
Right.
And that got the search for eventually discovery of Pluto. Clyde Tombaugh discovered Pluto
Tombaugh.
in 1930. And so from the Lowell Observatory. And so he found that. But then it turned out later on that when we got a better understanding of the size of Pluto, it actually wasn't massive enough to have these perturbations
On
on Neptune. So people have speculated since that time that there's another planet
Out there somewhere.
planet 9, because if you don't include Pluto, there's 8 planets in our solar system. So another major planet would be planet 9. And what you do in this case is to look at things that are way out there, like comets, like asteroids, like these objects that we're showing here. If they have an orbit that is peculiar,
That is preferentially oriented.
right, then there's some kind of gravitational perturbation occurring due to maybe a planet 9. So the fact that these 3 objects, without the discovery of this latest one, had all of the orbits sort of positioned to the lower part,
Preferentially located. Yeah.
yes, it wasn't random,
It wasn't random. Right.
suggests that there's a planet 9. So this new discovery, which shows that no, there are objects that have orbits, that are lined up so that they are above in this figure, that weakens the case for planet 9.
Right. So I know I was one of those that I will tell you that it's like this, folks. I will happily eat these words. But I think I've always thought it was selection bias that led to these objects having similar orbits, not that there was another planet out there. And this seems to indicate that, yes, it's a matter of we were looking in this zone for whatever reason. And so, of course, we found the 6 or 7 trans-Neptunian objects that were in that direction. We start looking elsewhere, we're finding objects that don't fit the mold.
And what tool now has just become at our disposal that we're going to search for evidence of planet 9?
Let's see. We've got James Webb, but we've also
just
got the
became
Rosa
available.
Parks.
Just became available. Rosa Parks.
No,
Which one is that? The Vera Rubin.
Vera Rubin.
Yes.
That's it, not Rosa Parks.
Vera
See,
Rubin.
I told y'all I'm terrible with names. I've got a collection of names in my head.
I was just
that
doing an
I'll-
experiment on you at work.
Oh, okay.
But the Vera Rubin
Vera Rubin.
is going to observe the southern sky like every 3 nights, over
Right.
and over and over and over, so you can see fainter and fainter and fainter. There's hope there that it will be able to discover evidence for Planet 9,
Planet
if it exists.
If it exists.
We'll see.
I'm dubious.
Now, if Planet 9 happens to be in the northern hemisphere,
Oops.
yeah, that's a different story. But the one thing that we can see, and that's the moon.
The moon.
And you might remember this story a little while ago, but asteroid 2024 YR4. This was the asteroid that at first got people all excited because there are indications that may have a non-zero chance of hitting the Earth in a few years. And then that chance increased slowly over time as new observations and new data became available. And that hit the public. Everybody got all excited about it.
Yeah.
And then when they got even more data, and especially data that was taken a while back, they realized that the chance of hitting the Earth is essentially zero.
Right.
But what they did discover is that it has a non-zero chance of hitting the moon.
Woo!
So this chance is about 4%. So take it for what it's worth. A 4% chance of this asteroid on December the 22nd in year 2032, and I plan to be alive still.
That's 7 years, so I should
Okay.
hopefully be around.
That's a lucky number, 7, right?
Right?
That this object, then, this asteroid, will collide with the moon. 4% chance. And you might say, okay, that's pretty small, shouldn't even worry about it. Well, 4% is 4%. It's better than 0 if you're...
It's non-negligible.
Well, yeah, that's it. That's right. So it may happen, but it's fun to think about what would be the consequence of it hitting the moon in 7 years from now.
6.5 megatons of TNTs.
That's what this paper shows. So the author of the paper is Paul Wiegert and Peter Brown and others. Now, Paul is somebody that I met. I'm not friends or anything, but I met him when I was at the University of Toronto, and he came through that system, and he's at the University of Western Ontario. Could be someone we could get on the podcast in the future.
Might try, yeah.
As a guest. They just put out a paper that calculated what would be the consequence if the asteroid did hit the moon. And as it says there, it would be equivalent to the release of 6.5 million tons of TNT.
That's a pretty big nuke.
That's a big bang.
Yeah.
Now, if this occurred, one of the things that they expect would happen is that the debris, of course, would be kicked up from the surface of the moon.
Mm-hmm.
And we are close, obviously, to the moon. There is a 10% chance in their simulations that debris would intercept the Earth in a few days.
That's kind of nifty, too. Because that would be both debris from the impactor and the moon. So, yeah.
And the other thing is that this material, because there'd be so much of it, a lot of it would go into orbit around the Earth, would not necessarily just hit the Earth, and that would be the end of it. And actually, they calculate that it would take up to 10 years for these small dust particles and stuff to get out of the vicinity of the Earth to basically, hit the upper atmosphere and burn up.
Cool.
And well, here's the non-cool aspect of it. The density of this material in Earth orbit would be non-negligible. It would be so much stuff up there, it would impact almost every satellite of appreciable size.
Oh, it would, wouldn't it?
Yeah.
Be a nice meteor shower for years, but at the same time, yeah, that's dinging all the satellites.
You remember the movie Gravity?
Yeah.
You remember where they had that exploding spacecraft in orbit and then all the debris
Hailed into...
circling around the Earth and then hit the space shuttle and the people that were there and all that stuff that happened. Yeah, that's the kind of thing you have to watch out for.
I didn't even think about that. I mean, the meteor shower would be cool and the material falling would be cool, but that part would not be cool.
Yeah, and in fact, a lot of that stuff would be floating around the moon and everything too. So
Yeah.
imagine you going to the moon on Artemis and you have to worry now about a debris field
Right.
that's in orbit around the moon.
Ugh.
And that stuff will get there's no atmosphere on the moon. So it's going to be there for a while and it'll be spread out depending on the radius away from the center of the moon.
Right.
So essentially you'll circulate all around the moon. So shields up when you're
Shields
heading to
up.
the moon at some point, right?
Need 16-inch battleship armor.
Yeah. Well, I mean, the orbit of the asteroid is well known enough
Right.
that you can even calculate where on the moon would this hit in 7 years. So here are the predicted impact sites on the moon itself. It's kind of cool you can do that so far in advance, right? But hey,
And
it's all
so-
gravity, right?
So let's talk a little bit about this.
Yeah.
Why is there a long string of it? Because that's a pretty long string. It's in a narrow band. But why would there be a string like that?
So that's the accumulated uncertainties
There you go.
of the orbit of the asteroid itself.
Because it's getting tugs from the moon. It's getting tugs from the
Yeah,
Earth.
and you
It's
don't
getting-
know it to the infinite, precision. So there's always an uncertainty of its location exactly.
But what this is showing is that the inclination of the orbit with respect to all the other bodies is pretty certain, but the exact speeds and everything are not.
Yeah, exactly.
So we've got a question: if it hits the moon, will it alter the moon's orbit? If so, what would the impact on Earth's tides?
So did you ever see Space 1999?
I did. As a kid, I grew up
Moonbase
watching
Alpha.
Yeah.
That's what's good. No, just kidding. Now, the size of the asteroid is too minor to do anything to the orbit of the moon that's significant.
As big as a 6.5 megaton blast sounds to us, compared to the size of the moon, size and energy of the moon, something happened.
Well, yeah, and it's not as if when we have earthquakes here on Earth, that alters the rotation rate of the Earth.
Right. So there will be effects.
There's an effect because we can measure very minute changes in things, right? So there will be changes to the moon's orbit, changes to the motion of the moon. As you said, the moon will vibrate for a long period of time. And
from what I remember of my classes on this subject, we can still detect the vibration, the motion produced by the asteroid that hit and produced the Tycho crater.
Right. Well, we've dumped, Apollo spacecraft equipment on the surface, crashed lunar modules that weren't used anymore after the astronauts transferred into the command module and dumped them on the surface just to test our seismometers that we put on the moon.
Right.
So all of that stuff, you can detect all of that stuff, but it's not going to have any significant effect to the orbit of the moon.
It's not going to blow the moon out of orbit or anything like that.
No, not like Space 1990. Then we could say they got it wrong by about 3 decades, but that's about it. Timing wise, right?
Oh yeah.
Anyways.
So yeah.
On to the next.
All right.
And this is related to, once again, proposed federal cutbacks. And this, wanted to say something about this because it affects NASA, it affects the space program, and it affects astronomy and astrophysics directly, as well as lots of other things.
It affects science in general.
Yeah. So this has consequences. Now, the proposed cutbacks have caused NASA to essentially allow early retirements to occur, force early retirements, whatever language you want to use, and get rid of people, essentially. Up to about 20% of the workforce. So that's up to 14,000 people, roughly, are leaving NASA.
Or is it 14,000 that are leaving or 14,000 that are going to be left?
Yeah, we'll take we'll reduce NASA's workforce by 20% to roughly 14,000.
Right.
Yeah.
So 14,000 will be left. But this means there were 18 to 20,000.
Yeah.
And that's expertise that's being lost.
That's the main thing. That's the main thing.
Just a huge knowledge base that we're just saying, well, thanks, guys. Goodbye. And that's why I'm saying it's going to affect science in general, because this astronomy may not seem like anything important to you, but the issue is that to overcome the problems in trying to observe these objects and everything like that, new computers, new detectors, new electronics have to be made, new materials have to be created, designed and created. And all of that is set back by the fact that we're not doing this other research anymore.
And it wouldn't be that big of a deal if there were no other countries in the world.
Right.
But there are, obviously. And these other countries are not going to do what we do.
Right.
They're going to push on their technology, their research, their discoveries in science and other things. And how do you know what comes along next?
There you go.
What's the next greatest thing? And if that's discovered in some other country that's not friendly to the United States, that can be a big problem.
There you go. So say what you want, but I like using the case of the anecdotal story about Michael Faraday. He was a pioneer in electromagnetic work. And the story goes that after one of his demonstrations before the folk of society, he was asked by a woman, of what practical use is this magnetism stuff? And his reply was apparently to go, "Madam, of what practical use is an infant?" The point being, the importance may not be in the here and now. The importance may be in its future potential.
Yeah. Good example of that. Einstein's general theory of relativity.
Right.
When that came out, he got a better new way of understanding gravity that seemed to be closer to the truth than Newtonian gravity.
Right.
And you might ask then, what use is this to be? Like, how does that affect? Does it lower the price of gas for my car? No, but it gives you GPS.
It gives you GPS, which does in fact lower the price of gas.
You
'Cause people
optimize
can
your journey.
Optimize the journey.
So in that sense, right, you never know what the potential of the discoveries made, what it pans out in the future.
Right.
So we should not be short-sighted in our
our view of these things.
Yeah.
Yeah.
And NASA, some people argue, is it's the only sort of agency in the federal government that returns more dollars in your investment. And some people had suggested, I don't know the numbers themselves, that for every dollar that NASA spends, you get $7 to $11 back in the U.S. economy.
Right.
So it's a money maker, not a net loser of funds.
There you go.
So why would you cut that?
But again, people see the direct things that are discovered and they're like, okay, yeah, so what? What does that have to do with me? And this asteroid impacting the moon, probably nothing, but
What other federal agency has it so that when you are on the other side of the world from the United States, there's somebody walking down the street in a city in the middle of nowhere or whatever, right?
yeah.
With a NASA on their T-shirt, right?
Right. The meatball. Yeah.
Yeah. What other agency has the merch that's spread around the world?
There you
So
go.
obviously people are inspired by what NASA has done in the past and what they can do in the future.
There you go.
So why would you cut the legs out from underneath that?
I'm mystified, but we got
Anyways.
people that think it's a good idea.
So we'll see how all this plays out, like I said, with the federal budget when we finally get to the approved version. Now, the last thing I wanted to mention today is we think about life a lot.
Right.
We've talked about this subject, whether there's life elsewhere beyond the Earth, hopefully more intelligent than what's on this planet, but when you look at the news. In order to find life elsewhere, one of the ways you can think about it is point of view of statistics.
Mm-hmm.
In other words, what is the chance of life elsewhere? Well, that chance could be based on what are the conditions here on Earth that have led to the formation of life.
Right.
Now, scientists at this point do not understand how you go from something that's not alive to something that is alive. What are the detailed steps going from A to B?
That's not to say we don't know anything. We know quite a bit.
Right.
We just don't know all the
It's a
deets.
work in progress. You've cut the science budget. It's a lot of work in progress. It's going to be for
Right.
a while, right?
There you go.
So we know some basic conditions. What are the basic building blocks or ingredients for life to arise on the Earth? And you can look elsewhere. Do you see these basic building blocks somewhere else in our galaxy?
And so we look for, do you see water? Do you see amino acids? Do you see complex amino acids, complex organics, which means complex carbon chemicals?
Now, what has been seen lately is a new paper that's come out, is the detection of 17 of these complex organic molecules, as they're called. And they found them using ALMA observations, which is a radio interferometer that's located on top of the Andes Mountains in Chile. And what they discovered was that there's a disk of material that's in orbit around this particular star in the constellation Orion. The star is V883, but don't worry about the catalog name. It's about 1,350 light years away, so it's not that far when you think about it. It's in our galaxy. And in this disk of material that orbits the star, and it's a young star, so we call this disk a protoplanetary disk, which means before the planets are formed that would orbit eventually this star. So it's in the very early stages of its solar system. Let's look at it this way. That they detected with ALMA then these organic molecules, and some of the organic molecules include ethylene glycol and, help me with this last name, glycolinitrile?
Close. Glycolinitrile.
Okay. And you can see the chemical formulas there. So these are actually special in the sense that they are the precursors
Right.
to the amino acids, which are some of the basic building blocks for biology here on the Earth for us.
Right. And we've found in our solar system outside of Earth all of the amino acid bases needed to form all the proteins, enzymes, DNA, RNA, all of mRNA, all of these amino acids necessary to build these things have been found in comet and asteroid debris in our solar system. So there's no reason to think, especially finding these things, that they're not present in this other solar system that's forming.
You know, radio telescopes have found literally hundreds of different molecules in space.
Now, I'm going to mention, we've mentioned spectra before. The spectra of these organic molecules are much more complicated than the spectra of, say, hydrogen or helium, because not only are there electron transition energy levels, but there are vibrations where the molecules are getting closer and further apart, and spin and rotation and chair modifiers where the actual structure is flipping back and forth. And so there's all of these little things, and these add lines to that spectra. And so start becoming, with the more complicated organic molecules, very difficult to differentiate.
Yeah, and the other thing is that's how we know the composition remotely of stuff.
Is through the spectra.
You don't need to go to the sun and taste it.
Right.
You can look at its light and analyze to find out its composition.
Right.
And that means if you can do it for the sun, you can do it for other stars. And if you can do it for other stars, you can do it to other places in our galaxy and in other galaxies as well.
And in other galaxies.
So the main point of all of this observation, at least to me, is that these complex molecules, which you need for life, as far as we know, at least life as we know it here on Earth, are everywhere.
They're everywhere.
They're everywhere. They're not unique to us, to our location. We find them in our solar system and beyond.
Right.
So if you have the raw ingredients spread throughout our galaxy, what's the chance that that stuff came together under the right conditions that ultimately produce life?
And hence my statement, is there life out there? Absolutely. Positively. It's out there somewhere else. The details of that life, I'm not going to speculate there, or I might speculate, but that's not for this show.
Yeah, that's a big question mark on that. But if you're interested in learning about biology, where did life come from initially? How did it start here on the Earth? What's going on elsewhere? One of the things you can do, of course, is to learn.
Pursue higher education and learn about this stuff.
Yeah, educate yourself. Be a lifelong educator. That's the way I like to think.
Yep.
You don't need to stop just because you finished high school. Go beyond that. And in fact, if you are in high school and you'd like to pursue, a major in the sciences or otherwise humanities, come to the University of North Dakota. We have a lot of really good programs, both online and on campus, that you could take. And if you're around, drop in to see us.
Drop in and see us.
We are here for you. And we'll do the best we can to make sure you enjoy your experience here at UND.
And I will comment on this one. Good question. Please do speculate. We may on another podcast, but not today. Not today, but we may do that, so stay tuned.
Yeah, definitely. And we could talk a whole hour. In fact, we should get a guest who works and trying to figure out how you go from something that's not alive like a rock to living creatures.
I'll have to maybe hook up with some of the biology professors here and see if they can suggest someone.
Exactly. Now, our next podcast will be next Tuesday, so that's August the 5th.
Is it August already?
August starts on Friday, Robert. And we teach class, and you got to teach labs near the end of this month.
Starting the 24th.
So get ready. Start preparing if you haven't already. So the summer is going really fast. Always does.
Always does.
And the winter drags around here. I don't know why. But it drags because
I know why.
But it drags
cold,
is a good thing
because
we have such a good time here when the students are around. So we want the winter to drag.
Okay, you're right.
Okay?
You're right. It does make the time go more interestingly
when
students are around.
Now, we always leave you with a quote at the end of our podcast. Today's quote is by Clyde Tombaugh, the person who discovered the planet Pluto in 1930. And we talked about objects beyond Pluto and so on, so it's relevant to this. So here's a quote. I may have discovered a planet, but the real achievement is the inspiration it provides to future generations.
Oh, Bravo.
Very
Yeah,
nice.
that's great.
Now, if you like this podcast, please give us a thumbs up. Smash that like button, as they say.
Yep.
And subscribe if you haven't subscribed. Maybe tell all your friends what a great podcast this is to get them to view it. By the way, if you have any ideas of things that we'd like to cover in the future podcasts,
Give us a comment.
yeah, put some comments down and let us know, and we'll dig up some experts in those fields and get them on.
I'll try to at least.
Yeah, for sure. So anyways, thank you very much for watching, and we'll see you next time.
Thanks, folks. Have a good one.